Okay, so I'm going to start with some properties we've got of this simplicial functor. So we've already seen what pi naught is. Pi naught of the simplicial set, once you work through the definitions, ends up being exactly that. So you take elements in degree 0 of the simplicial set, or that by the equivalence relation from degree 1. So it's exactly the deformation functor. We've also got some good properties with respect to small extensions. So before you remember with this, if we had acyclic small extensions, it mapped them to isomorphisms. Now we have that if a map from A to B is an acyclic small extension, the map from F of A to FB is a weak equivalence. In other words, isomorphism. Pi naught and the higher homotopy groups. Oh, MC here, yes, thank you very much. And there's something I might as well mention this now, but I won't write it down. If you're restricting to DG plus art, so if your DG algebras are in non-negative chain degrees, then actually any surjective quasi-isomorphism, so any surjection which is an isomorphism of homology groups, you can break down as a composition of acyclic small extensions. But in fact, that's not true on the bigger category, on that category DGR with potentially negative degrees, when there are some quasi-isomorphisms which you can't break down this way. So this in fact ends up meaning that it does preserve quasi-isomorphisms in DG plus R, but not in DGR. And that's a feature of the homotopy theory of DGR, actually, that its notion of equivalence has to be finer than quasi-isomorphism. But there's a reason I haven't written all that down, which is that it's a really subtle point. But I thought I'd mention it sometime. Right, so what happens if say we take something that's just an Artinian ring, and say our DGLA has no negative terms, which is typical for some deformations of most algebraic structures. This is what you get. The Hochschild complex that I looked at yesterday actually violates this because it had that term in degree -1, which was corresponding to the inner automorphisms and was giving that annoying curvature. But if you just get rid of that term, then that would also satisfy this condition. So then what happens is we get that I1 of this Maroc-Cartan factor at a point X is isomorphic to, so it's elements of the gauge group which fix X. In other words, automorphisms of X. And all the higher orthogonal groups vanish. Whereas in the case of the Hochschild complex, we actually do get a pi 2. Get a pi 2 corresponding to inner automorphisms of an algebra. So if your algebra has non-trivial inner automorphisms, then this picks that up. And it's because you're. And so what's happening here is that these simplicial sets, which are sort of a model for homotopy types of topological spaces, are also modeling infinity groupoids in some sense. So we've got objects, we've got morphisms, and potentially we've got higher automorphisms. But it's often well, topological spaces are quite one of the more familiar models for infinity groupoids. It also means that given any two objects in this, so any two Maroc-Cartan elements, you can look at the path space and maps between them, and that's sort of giving you an infinity groupoid structure, and then the homotopy groups of that are the encoding higher morphisms potentially. Okay, so if we can look at, so we had tangent spaces before, so let's see what they give us now. This is where take epsilon n in degree n, necessarily square 0. We look at getting a simplicial set here, and take its homotopy groups. And what we get is sorry, there's an entire index missing there. So when we know that when I is 0, we know that this is def, and it's going to give us n plus 1. In this case, we get n plus 1 minus I. So that first example tells you what happens if you feed in Artinian rings. Once you start feeding in rings with extra structure, more complicated TG algebras, basically what's happening is that the further this goes down the chain complex, the higher the cohomology groups it picks up over here. And in fact, if I come back to this example here, so we've got A Artinian, no negative terms, and in fact what happens is that this is equivalent to the nerve of gauge group acting on the Mallet-Canton set. So don't worry about that if you don't know what a nerve is. It's the, well, I suppose I can actually write it out. We get this in degree 0. Product in degree 1, where one of these maps is projection, the other is the gauge action. My C's and L's are becoming very similar, aren't they? In fact, there is a more general way of looking at so this phenomenon does actually generalize. No, two minds as to whether to mention it, but so in general, I've actually got equivalences. Take the homotopy quotient by the gauge action, and that actually turns out to be completely harmless, this set. So it doesn't change the homotopy type. And then there's another equivalent thing within that. So we just take this set, the Mallet-Canton set, and quotient by elements of this simplicial group whenever they're still landing up in that set. So this.
So what is gauge was simplicial motion?
Sorry, what's the question?
Simplicial motion gauge.
Exactly what you think it is. So you know what this is. So in level N, you take L tensor. Yeah. So in fact, this simplicial set we've had, we could think of it as the nerve of the simplicial groupoid, if you like, where you have this set here and this simplicial set, this simplicial group sort of acting on it, except that you ignore anything that lands up outside the set you want to work with. So, and quite often this description in specific examples is a lot easier to think about, in that the objects are exactly what you're expecting them to be, and then we've got various higher automorphisms. But I'm being deliberately vague here. Let's just... Right, so now... Okay, so I've mentioned... Okay, I think we're overdue an example, aren't we? Let's take that very simplest example, where we just have endomorphisms of V concentrated in degree 0. So we saw that the pi naught of simplicial thing is just the deformation factor. So this is as before, it's just modules deforming that. And then to work out what pi n is, you have to look at it as a given deformation x. where so then what you get is it ends up being an X group. Minus n. Basically, okay. There's a somewhere. So that's right. So if we call, say, deformations M of that module, and then at the class M, these homotopy groups are picking up the X groups. More generally, for algebras, it's picking up things like higher derived derivations, higher automorphisms. When you've got a Boolean structure like this, so the higher and lower automorphisms are things you have seen before. Right, so now, what time did I start?
15 minutes ago. It's late. That's last part.
Okay. So 5 plus 12, not bad. It's just, is that, so 12 or 5 is what I'm fit, is that what you said?
We go until quarter or 20 past.
Okay, so 20 past is what I'm, okay. So, completely lost track of time. Right, so what I'm going to do now is show how we can actually recover everything. Just so once we've got these simplicial functors, we can restrict to sort of nicer class of C rings, and we already know that. So I mentioned it. So things like quasi-isomorphisms get set to weak equivalences by MC, which doesn't happen on the bigger category. And we've already seen that that bigger category has some quite pathological properties. So what allows us to do this is that, okay, so to summarize some of the properties we've got. First of all, if we have a diagram like this of topological spaces, a homotopy final product noted X cross H, Y, Z. The model with anything homotopy equivalent is permitted, but specific model is this. So this is saying, so a point in this space is a point in X, point in Z, and a path between their images in Y. Because it has to be something that behaves well up to homotopy. So we can't ask that 2 points have the same image in Y, there just has to be a path between them. And So, important property this has, which is that you then get a one exact sequence of orderly groups and sets. I remember when I started out in this subject, it was a real nuisance trying to find any decent references on Whittleby limits, because other products was all I was really interested in as a deformation theorist, and the literature only ever tended to give general limits over an arbitrary category. And so I had to sit down and try to work out what that meant for the examples I was interested in more concrete form. So we have a long exact sequence. And you can deduce this by combining long exact sequence for a vibration with various other bits and pieces. It goes exactly as you'd expect. You have this, plane of this, it maps to pi n of x, pi n of z. And the images agree in pi n of y. So it goes on, and I will just tell you what happens at the end of the sequence. So you have the fundamental group of y acting on path components, flat product. And it's acting transitively on the fibres. There the sequence stops. So there's no guarantee at all of any sort of sensitivity. And you might remember those exact sequences I wrote down for the deformation functor. They were quite similar to the first terms we're seeing here, where you had things like H2 in here. I suppose it was a slightly different thing, but it tended to be where we had def LA, def LB, and H2 there and H1 there. And that's actually exactly something of this sort of flavour, and you can try to show you how you can deduce that from these sorts of things. So now there's a analog now of the property we had previously of being a deformation functor, which is that I'm not going to prove this, but so I'll just state this. So since so if we get this thing here, so it has the following property. So if we have small extension A to B and an arbitrary map C to B, then we can at the value of Mercantile on this fibre product. And that also maps to the homotopy fibre product. So I've defined the homotopy fibre product in topological spaces. To geometrically realise everything for that to make sense. So I'm saying for each of these simplicial sets, there's an associated topological space. And then, so this topological space here maps to each of these. And we look at this homotopy fibre product. So where we've got points in here, paths between them here. And this is a weak equivalence. Isomorphism on homotopy groups. And from this, if you think about it, just from that property, you can deduce FL as a deformation function. Oh, I suppose there's one other property we need, isn't there? So that implies deformation factor 1A and 1B. So, whereas condition 2, you could deduce from the fact that MC sent acyclically small extensions to weak equivalences. Because you see what happens. So what happens is, what do we get when we take path components here? So here we've got two equivalent topological spaces, homotopy equivalent. So on the left, I naught this, well, that's just deformation factor. Right, that's isomorphic to pi naught. This homotopy fibre product. And what can we say about this? So we want to compare this with FLA by FLB, FLC. You know that this is where each of these is the respective pi naught. So what does this tell us?
Does it vanish or something?
So this just tells us that this has to be surjective. So this is an exact sequence, saying that if I've got something in here, something in there and there, which agree in there, it's one image of that. So it just tells us that that's surjective. If we knew pi1 vanished, we'd have an isomorphism there. But in general, it doesn't. So all we can say is that that's surjective. But if you remember the definition of a deformation functor, and you've seen a lot in the past days, so you might have forgotten it. But it was precisely, so what happened was condition 1a was exactly saying this is surjective. 1b was saying if we took the product over k, we would just get a product. So that's 1a. 1b is simpler. 1b is just that's good. It's applying to the product. Well, that just means we've got the product of the maximum ideals. So this thing is and therefore when we take pi naught, so in fact what's happening is that those properties that Manetti used to isolate properties of deformation functors are exactly capturing how pi naught behaves under homotopy fiber products. So it's in general it's just surjective like this. But if you've got a straight product rather than a fiber product, then it does give you an isomorphism. So if you just take product two spaces, then pi naught is that. And so that means that so stick with the notation I used in my paper. So I'm going to let script S for Schlesinger, because Manetti's deformation functors were a derived generalization of Schlesinger's conditions, and this is a sort of further derived homotopical version. So let S be the category of functors. Going from, it's going to be from DG plus R to a simplicial sets, such that two properties one is good behavior under fiber products, equivalence, or small extensions. And the second property is that the maps of weak equivalent are always cyclic small extensions. So we've seen as an example that the Marocatov functor of a DGI satisfies these conditions. And you might wonder what else does, and the answer is essentially nothing. So we have pointed from DGLAs to this category. So this gives this homotopy categories. So here we're saying quasi-isomorphisms. It's H star equivalences. And here we're saying weak equivalences. In other words, maps. So if we want to regard a map of DGLAs as being an equivalence to isomorphism on cohomology, a map of these functions an equivalent if it's giving us homotopy equivalences at each point. And it turns out that everything is of this form. And I suppose, in case anyone's worrying about where an infinity algebra is fitting in this picture, well, every infinity algebra is quasi-isomorphic to a DGLA. So, back to there. And you've probably noticed that almost everything I've done today works for infinity algebras just as well as for DGLAs. So, as an aside, we could fit an infinity in here as well. They're all equivalents. And so, Lurie calls this category S formal moduli problems. Which is not a name I like because a huge proportion of deformation theory literature is in, you start from a moduli problem, so moduli of some algebraic or geometric structure, writing down the functor you work with, trying to prove it satisfies stress conditions. And these are homotopy algebra with Schlessinger's conditions. So if you call these formal moduli problems, then you're trying to show that your formal moduli problem is a formal moduli problem. And that summarizes decades of. So it makes the theorem sound more impressive if you say, look, the homotopy category of DGLAs is the same as the homotopy. DGLAs is the same as formal moduli problems. But somehow it then makes it harder to talk about some other stuff.
So the equivalence, is it equivalent equivalence immediately, or will it just model structures?
Yes, there are model structures and it's equivalent. It's equivalence. So it's not just homotopy categories. if you want to, you can infinity localize and you get an equivalence of infinity as well, but that follows from the equivalent equivalence. God. Overrun often enough. I think that's a sensible place for me to stop today, but yeah, so
Thank you. Are there any questions?
I have a technical question about you ran the model of homotopy in fiber products.
yeah.
And in general, we choose a resolution such that the three are all okay. One error is the subtraction, vibration.
Okay.
Yes.
So you can write it as a fiber, and then this arrow is automatically a vibration.
Okay.
And I had to use topological spaces for that because all topological spaces are fiber, unlike whereas, well, not all topological spaces are color fiber. But geometric realizations always are.
More questions? Okay, let's take the.
Oh, sorry, there was a hand.
Sorry.
I'll ask that.
Okay.
Okay, let's thank Jon again.